So let's do another exercise, and let's do exercise 3.12, which deals with the properties of the SES utility function. As you learned in the lecture, the SES utility function is a very general utility function, and both the Cobb-Douglas, the perfect complements, and the perfect substitutes case are special cases of the SES function. I also refer to the note that I posted in the electronic learning environment about the relationship between the Cobb-Douglas function and the SES function. But I think it's very instructive to go into the properties of the SES function, as we will do in this exercise. So we have the SES utility function that is given, and we have to first show that this function is homothetic. And we do so by answering the question, how does the marginal rate of substitution depend on the ratio of y and x? So the SES utility function as given is u x y is alpha x to the power delta divided by delta plus beta y to the power delta divided by delta. This is the SES utility function for values of delta unequal to 0. And we have that the marginal rate of substitution is the partial with respect to x divided by the partial with respect to y. And just doing that, it's not that complicated, because if we take the first derivative with respect to x of the utility function, we arrive at alpha x to the power delta minus 1. Taking the derivative with respect to y, we get by to the power delta minus 1. And we can rewrite this as alpha over beta times x over y to the power delta minus 1. And as you can see, the marginal rate of substitution only depends on the ratio between y and x, which means that the underlying utility function, the SES utility function, is homothetic. And that completes exercise A. So that allows us to continue with exercise B. And in B, we have to show that the results from part A agree with our discussion. So the discussion in the lecture, that the case with delta equal to 1 is the case with perfect substitutes, and the case with delta equal to 0 is the Cobb-Douglas case. Well, if delta is equal to 1, then the marginal rate of substitution reduces to a constant, and this constant is equal to alpha over beta. Yeah? So just plugging in delta 1 over here, and we arrive at x over y to the power 0. So independent of what x and y are, this one is equal to 1, and we are left with alpha over beta. And this is really the case when two goods are perfect substitutes. So we have that this is a constant. It's the case with perfect substitutes. And if you really want to check this, in the previous exercise in 3.7, in A, we had the case with perfect substitutes, and we also found that the marginal rate of substitution was constant, namely equal to 1/3 always. So you can compare this to your outcomes in exercise 3.7a. Then the other case where delta is equal to 0, if we plug in that value, then our marginal rate of substitution is equal to alpha over beta y over x. Again, we plug it in over in this expression over here, delta equal to 0. We get this term within parentheses to the power minus 1. So the x and the y flip, and we get y over x as a result. And this is the exact expression that we obtained in exercise 3.7b, which is no surprise because in that exercise we had a Cobb-Douglas function. So if you want to see additional proof, just look back at the notes of exercise 3.7b. Okay, so those are the questions A and B, and that allows us to continue with C. And C is show that the MRS is strictly diminishing for all values delta smaller than 1. Now, best is to start out with our marginal rate of substitution and the functional form within the green circle over here. And it should be diminishing for any delta smaller than 1, meaning that if we would take the x higher, then the marginal rate of substitution should become smaller. Now, that says we have to check whether if we take the derivative of the marginal rate of substitution with respect to x, whether that thing is smaller than 0. Now, if we take this derivative, then we have the d minus 1 in front of the equation. So we have d minus 1, then the alpha over beta, y to the power 1 minus delta, and x to the power delta minus 2. Now, is this smaller than 0? We know that we need to have non-negative units of x and y. Suppose that we have an interior solution, and this one will be positive. Alpha and beta are also positive because we have a Cobb-Douglas. So the only way in which this term can be negative is when the first term in the expression, delta minus 1, is negative, and that only holds if delta is smaller than 1. So the marginal rate of substitution is diminishing if and only if delta is smaller than 1. That is exercise C. Then in D, we need to show another property, that if x is equal to y, the marginal rate of this function depends only on the relative sizes of a, alpha, and beta. Now, that is really easy to see, because if we take the marginal rate of substitution and we have that x is equal to y, then this entire term, x over y, becomes 1. We can take 1 to the power anything. It doesn't depend on the value of delta, but the result will be 1. So if x is equal to y, then the marginal rate of substitution is equal to alpha over beta. And it does no longer depend on the exact value of x or y, but they need to be identical to each other. So that is D. And then the most interesting part is question E. Calculate the marginal rate of substitution for this function when y over x equals 0.9 and when this ratio equals 1.1. For two cases, delta is equal to 0.5 and delta is equal to minus 1. And what, from these numbers that we will get, what do we conclude about the extent to which the marginal rate of substitution changes in the vicinity of x is equal to y. And how would you interpret this geometrically? Now, this is typically the question that you find difficult to answer, but you need to know what is asked for. And I will solve this just making a table, because part of it is just bookkeeping. So we need to compute the marginal rate of substitution for this ratio being equal to 0.9 and a delta equal to 0.5. So, and also for this ratio being 1.1 and the ratio being, or delta being 0.5, then 0.9 and minus 1, 0.9 and minus 1. Now then you can compute. So delta equal to 0.5 means that you have a square root, and the marginal rate of substitution is equal to alpha over beta, and these numbers are not given in the exercise. The ratio is 0.9, delta is 0.5, so we have marginal rate of substitution is alpha over beta times the square root of 0.9. And if you do this calculation, it's about 0.95 alpha over beta. Then in the second expression, the delta is the same, but the ratio is 1.1. So the marginal rate of substitution is alpha over beta square root 1.1 is about 1.05 alpha over beta. And then for the same ratio, this ratio should not be 0.9, but it should also be 1.1. So for the ratio being 0.9 and the delta being minus 1, plugging that in, we obtain alpha over beta 0.9 squared, because the expression is, the power is delta minus 1, and if we take delta equal to minus 1, we get the power minus 2. So, and that one is, well, it's not almost identical, actually. It's exactly identical, so we can write an equal sign here. 0.81 alpha times beta. And finally, if the ratio is 1.1 and the delta is minus 1, we get alpha over beta. 1.1 squared is 1.21 alpha over beta. And now it's important to remember again that the marginal rate of substitution is identical to the negative of the slope of the indifference curve. So let's map this in a figure. And I already did some preparation here. So here you see the x and the y-axis, and I've drawn two black lines, and they correspond to the ratio in which x and y are consumed. So you can see that in the first black line corresponds to all consumption bundles in which y and x are consumed in a ratio 11 over 10, so 1.1. And the second black line corresponds to all consumption bundles in which x and y are consumed in a ratio 9 to 10. And then going back to our table, we know that if delta is equal to 0.5, so the first two expressions, so look at the first two expressions, then if we move from the one black line to the other, so if we go from the ratio 0.9 to the ratio 1.1, then the marginal rate of substitution substitution changes, but not that much. So if we go from the 1.1 line to the 0.9 line, so if we move from here to there, then we experience not that much of a change in the marginal rate of substitution. So we go from 1.05 alpha over beta to 0.95. So the delta, the change, is relatively small. But if we look at the situation where delta is equal to -1, we observe that we have a much more of a change in the marginal rate of substitution, because we go from 1.21 alpha over beta to 0.81 alpha over beta. So here is the change sizable. And given that the marginal rate of substitution says something about the slope of the indifference curve, it means that in the second case we have much more of a change in the slope of the indifference curve. Now, to depict it in the figure, so the delta equal to 0.5, suppose that this would be a point on that indifference curve, then we have a gradual change. So we have something like this. For the delta is equal to 0.5. So at this curve where the indifference curve intersects with the ratio 1.1, black line, there the marginal rate of substitution is a negative of the slope of the indifference curve. And also at this other point, and you can see that between the 2 points, there's only a minor change in the marginal rate of substitution. But the change is much larger if we have the delta is equal -1 change. So that indifference curve will look something like this. So delta is -1. Again, where the indifference curve intersects with the ratio 1.1 black line, the marginal rate of substitution is a negative of the slope. So something like this. And we see quite a bit of a change in the marginal rate of substitution when we move to this other slope. So it will look something like this. So what you can see is that if we lower the value of delta, if we go from 0.5 to -1, then the goods become less of substitutes for each other. And at the extreme case, if we would take delta equal to -infinity, so well, let's do this a little bit nicer, -infinity, then we have the situation of perfect complements. So, and what this exercise shows you is that by changing the value of delta, we in fact change the in how much the two goods x and y are substitutes of each other. And I think that is really important to see, and also how flexible this SES utility function is. And this completes exercise 3.12.